Hello guys, today I am going to continue with a series of videos and I'm gonna be working with this problem and this problem deals with the calculation of internal forces. So for this problem what we have to do or what is asked is internal forces and remember, when I say internal forces, I mean forces and moments, internal moments. Where? At these 2 points that are marked here, at A and B. This is what we have to do, A and B. Okay, let's start with those calculations. The first thing that we have to do, like almost in every single problem, almost I say in variable, is calculating the reactions using the whole body structure, the full structure. So if we do that, the first thing you have to realize that this support here is a pin, and as you know, and you should know like by memory, not even thinking about it by now, a pin produces either one reaction with a known line of action, but for our purposes we always say that it produces 2 reactions, one horizontal reaction and one vertical reaction. I'm going to name these supports like C and D, and I'm going to name this point here as E also. So whenever we do that, these values, this reaction here is going to be then Cy, and this reaction here is going to be Cx, and this other support here is a roller. And for the roller, we are going to call that dy. Remember, the roller produces one reaction perpendicular to the line of action, to the surface where the roller is acting. And these are my 3 reactions here. 3 reactions, unknowns in this case, 3 equations of a static equilibrium for rigid body equilibrium. That means that we can solve this problem. You have to notice something. This is a tension here. But while this is attached at both ends and I'm not cutting anywhere, I'm not doing any section, that is an internal force. Exactly as if I'm dealing with this member or this member or this member. So you don't take that tension into account like an external reaction, and you don't count them here. So how are we going to solve this? We're going to do summation of forces first, calculate the reactions. And the first thing that we do when we calculate the reactions, I'm going to change the pen. I'm going to use the black pen. First we do summation of forces in x equals 0. And I have Cx. And I have this 600 Newton force here equals 0. And that means that Cx is going to be negative 1600 Newton. Or Cx is going to be 600 newtons, I'm sorry, 600 newtons, and Cx is going to be 600 newtons acting to the left. One thing that I always do when I have this, immediately I come here and I change that direction, because then otherwise I'm going to forget that I changed the direction. Okay, summation of forces in x. Now if I do summation of forces in y, immediately I'm not getting any because I still have 2 unknowns, so I'm going to do summation of moments. And summation of moments where? Well, I can do summation of moments actually at any point, but if I do summation of moments here, I think it's a little bit easier to solve for now. Less calculations. And summation of moments has to be 0. If I do that, I have this force, 600, multiplied by this distance, horizontal force, vertical distance. That distance is 0.4 plus 0.6. I'm going to copy like that so you can review it later. And if I am assuming that this rotation is positive, well, if I put a pin here and I pull, the rotation is going to be happening in this direction, which means it's going to be a negative direction for the moment. What else do we have for the moment? This other force. That force is dy. And the distance now, because the force is vertical, the distance has to be horizontal from this point to this point. And that distance is 0.4 plus 0.4. And in this case, the rotation, when I push this in this direction, rotation is going to happen in this direction, which is counterclockwise. And it's positive because that's what I assume to be positive. I don't have anything else, equals 0. And from here, you can solve for dy. You just pass this to the other side. You're going to have 600 times 1 is 600 divided by 0.8. And that's 600 times 1 divided by 0.8. Yes, that's 750 Newton. From time to time, remember, every time that you box a result, put the units. Okay, now we have Cx and dy. I only need to calculate Cy in order to complete my reactions, and that's going to be done by doing summation of forces in y equals 0. And summation of forces in y equals 0 then will be Cy plus dy, and I don't have anything else, equals 0. Or in other words, Cy plus 750 equals 0, or Cy equals negative 750, or Cy equals 750, but because I assume it here going up, and it happens that it's negative, it's going to come down. And remember, the units are Newton. What do we do now? Immediately, once again, immediately you get that negative sign, change in your diagram here, your reaction. Because later you might, and you will, forget, trust me. Okay, now we can focus on what the problem is asking us to do. The problem is asking us to do, calculate the internal forces and moments at A and B. If it was me, and this is a test problem, an exam problem, and the internal forces at A and B were the same, I don't even gonna think about it. I'm gonna start by doing summation of forces at, internal forces at B, because it will be a lot easier to calculate the internal forces at B. Look, I just have to do a cut there. So let's start with internal forces and moments at B. For the point B, what do? You do a section over there. If you do that section over there, what you're going to have is this. This distance is 0.2 meters, and I have a reaction dy in this part, and that reaction dy is 750 Newton. Now look the side that we are selecting. We are selecting the right side, and if you remember, I told you that the reactions have to change, and the direction of the internal forces change according to whatever side we are studying. The moment is going to be like that. If I'm in this side, the moment is going to be like that. If I'm in this side, the moment is going to be like that. If I'm in this side, the positive direction for the shear is going to be like that. If I am in this side, the positive direction for the shear is like that, and the axial is going to be like that, and the axial is going to be like that. We explained this in class for the moment shear and axial. Well, it happens that I'm in this part, I'm studying this section. If I'm studying this side, I have to use this as my positive convention. So I'm going to put here that my shear at B is going to come in that direction, and my moment at B is going to go in that direction, and my axial at the point B is going to go in that direction. And now we do summation of forces in Y equals 0. And if I do summation of forces in Y equals 0, what we get is V, or shear at B, plus 750 equals 0. So my shear at B is going to be negative 750 Newton. Remember, in this case, I don't change anything for now, because the only thing I'm interested in is knowing the result. That's it. It's a negative force, so I'm going to use a negative value. 750 and 750 is negative. Now summation of forces at x equals 0. And if we do summation of forces at x equals 0, the only thing that I have, the only force that I have is A, the axial at B equals 0. And now we do summation of moments. I like doing summation of moments always at the point where I'm doing the section. So summation of moments at B equals 0. If I do that here, then I have MB, which is going to be negative. Why is negative? Well, it's negative. Don't get confused. Remember, I say this is the positive direction, but when I do the summation of forces, this is my assumption. So this, according to this assumption, this is going to be negative, negative MB, and this is going to be plus, because it's going to be rotating in this direction. 750 times 0.2 equals 0. So my moment at B is going to be 150 Newton meter. Look how easy it is just to calculate the internal forces and moments at the point B. If this is a problem and the problem is scored half and half, well, we have half of the problem done. Half of the problem is solved, and we have half of the point. Probably this is not going to be like that. If I was asking for this problem, I will assign a bigger grade to this point, to that point. Why is that? Well, because now, in order for doing this point here, the internal force at A, I have to make a section also. I keep the whole structure complete, but now I'm going to make a section. And when I make a section, I can't just section this part without cutting this. So I have to make a section and isolate one side completely of that structure. So when I do that, if I copy that side of the structure, I'm going to change the piece of paper. If I copy that side of the structure and I copy it here, then look what we have. We have this section. This distance is 0.2 meters. I have this tension over there. Here, I'm going to have my internal reactions be at A, my axial at the point A, and my moment at the point A. And here, remember that we switch because they were negative, and that's the idea of switching it, that you don't forget it here. Then you're going to have the point C, and this is 750 in this direction, and this is 600 in the other direction. But now if you realize, and you can, we have 1, 2, 3, 4 unknowns. So that means that we don't have the value, or we can't solve this immediately just by doing one section in the way we did it. We have to do something else for that. I'm going to need to calculate some angles, so I don't know if it's worth it to do it immediately. But we can do it. Let's say, well, let's move to this side. It doesn't matter. How do I calculate this? Well, then I go and I see this portion of the structure. Look at this part of the structure. And I'm not talking about making a section in this beam. I'm talking about this member in it. I'm going to take only this part, that member, the member EF, this member EF, and I'm going to take that member out, and I'm going to do an analysis only in that member. If I do that, that will be the member EF, and here it will come the tension T, and here, what type of support is that? It doesn't say it, but you can see it there. That's a pin. It's a pin support. Well, if it's a pin support, how many reactions I'm supposed to have? I'm supposed to have one reaction EY and one reaction EX. Also, we have this force applied here at the center, which is part of the section, and that's 600 Newton. And the distances are 0.4 and 0.4. And what else? Well, I had the distance that goes from this projection here. This distance is 0.4. Why that distance? Well, because that distance is going to allow me to calculate this angle alpha, and I can say that alpha is equal to the inverse tangent of opposite divided by adjacent, so 0.4 divided by 0.8, or alpha equals 26.57 degrees. Now, here I have 3 unknowns. So if I do read body equilibrium in this part, I can solve for it. If I do summation of moments at E directly, or I can do summation of forces in X, or I can do summation of forces in Y, that is going to allow me to calculate this. I'm going to do summation of forces, summation of moments at E, because I like that. But if I do whatever of the other 2 equations, I will get it at once. Well, I wouldn't get it at once because I have EX plus T, and then I have EY plus T, and then when I do that, I have 2 unknowns in each one of them. But if I do moment at E, that's going to give it to me immediately, the value. Summation of moments at E equals 0. The only component that is producing moment for that T is the horizontal, because the vertical is passing through the point. Remember, transmissibility principle is passing through the point. I'm calculating the moment. So this component is going to be T sine of the angle, because that component is the same component as if it was here. So it's going to be T sine of alpha. And the rotation, if I push it in this direction, is going to make a rotation counterclockwise, which I assume it was positive, so I'm correcting this part. And then I have this force, which is 600 horizontal force, vertical distance times 0.4. And if I put a pin here and I apply in this direction, it's going to rotate clockwise, which I said is negative. That's going to be equal 0. Remember, alpha is this angle here. And then you can calculate your tension. And your tension is, this is not 0.4, I'm sorry. Yeah, it's 0.4. 0.4. And then oh, but I didn't multiply here by the distance. This is T sine of alpha multiplied by 0.8. Sine of alpha multiplied by 0.8. I was explaining just this force, but I didn't explain that this is multiplied by 0.8 here. 0.4 plus 0.4, 0.8. So when you do the summation of moments here one more time, you say T sine of alpha multiplied by the distance, which is 0.8, and 600 multiplied by 0.4 equals 0. And then you solve for T, and T is going to be equal to 600 times 0.4 divided by 0.8 sine of 26.57 degrees. When you do that, you get that alpha is going to be, T is going to be equal to 670.7 Newton. Now we have the tension T. Now we can proceed to this side. But before we couldn't, because I had, remember, 1, 2, 3, and 4 unknowns. Now I'm going to put this T in that part, and I'm going to refer to this portion of the diagram. Guys, remember one more time, remember this part, T sine multiplied by 0.8. Okay, now we know this T, and this T is 670.7 Newton. Now we can calculate these forces. How do we calculate those forces? Well, we can start by doing summation of forces in X equals 0. Summation of forces in X equals 0. What forces do we have in X? Negative 600 plus this component. What is this component? 670.7 multiplied by, now if this is alpha here, this is going to be alpha here, because remember, both this angle here has to be equal to this angle here, and this angle here is alpha, which is this one at this end. So the horizontal force is going to be this one, or it's going to be this one, which is the same. So meaning that This is going to be 670.7 times sine of alpha minus, and this is plus, and this is plus also because it's going to the right, AA equals 0. And from here, you can calculate AA, which is going to be equal to 300 Newton. What do we do after that? We can do summation of forces. Yes, we can do summation of forces in Y equals 0. 750 negative plus, because remember, now we're talking about the vertical component of that tension. It's pointing up. Multiplied by cosine alpha minus VA equals 0. Alpha, we know it, one more time. And then when you calculate that, you have that VA is going to be equal to negative 150 Newton. You have to be really careful, guys, really careful with these positive and negative signs. I know that you are in a rush most of the time and you want to calculate this, and then you do it in your calculator in one side and you forget to pass to the other side. Maybe it's worth it, I don't know, maybe it's worth it that if you have it like that, the equation, solve for VA. It doesn't matter that you think that you know what you're doing. Solve for VA and pass it to the other side and try to solve it, and then apply, say VA equal, pass this to the other side, negative 750 plus 670.7 cosine of alpha, and then solve it instead of solving it here, because I know that most of the time you forget to pass it to the other side. Okay, the last part that we are missing is summation of moments here. So I know I said before that I like to do summation of moments at the point, but look, I can do it at the point, and then this force will be producing, this force will be producing, and this force will be producing also here. But what if I decide to do it at this point this time? I don't know, I'm going to try to do it here. That point I call it F. So I'm going to do summation of moments at F, because I want to, that's it. You can do it here if you want to. You can do it here. You can do it anywhere. You have every single other value. But I think that if I do it here, I eliminate more calculations. Then this force is not producing, this horizontal one is, this vertical one is not producing, and this horizontal one is not producing moment. So the only thing that is producing moment is, start with this, MA, which is positive because it's assuming this direction, negative VA times 0.2, and then negative also 600 times this height, and this height is 0.6. Equals 0. Remember VA we just calculated now is negative 150. Careful here, very careful here. You have to have a lot of care and be extremely cautious with this one. Once again, I advise you to solve for MA. So solve for MA is going to be equal to 0.2 times VA plus 600 times 0.6. Now MA is going to be equal to 0.2 times VA, but VA is negative 150 plus 360. And MA is going to be then 360, this is 30, and this is negative 30, this is positive 360, so 330 Newton meter. And that will be the end of our problem, because in summary we calculated internal forces at point B, which we could do because we just did reactions at the end with the whole element. We did reactions, the whole structure, and then we made a cut here. Remember, when you do the cut here, the direction of the internal forces has to be according to the side that you are using in order for you to put the correct convention, the positive convention of the internal forces and moments. So we did that and we calculated B. The problem is that when we went to the other side and we want to calculate A, and we did the cut here for calculating A, we had more unknowns because we didn't know the value of this F. Then we use our knowledge, because you already know that you have this point here and this point here and this element, and this is a pin, and this is basically like a pin. And if you have an element that is pin, or is only a pin, but you have forces at the ends, that works like a rigid link, or that works like a truss element, because if you, well, in this case it doesn't work like a truss element because you have this force in the middle of the structure. If you didn't have this one here, yeah, it would be a rigid link, or it would be a truss member, but you have this force here. But what I know is that I have two reactions here. If I have two reactions here and one here, once I take the free body diagram of that element, I can get for solve for the tension, put the tension back here, and solve for my unknowns. Well, that's basically the result of this problem. We calculated, as I said before, the forces at point B and the forces, internal forces and moments at the point B as it was calculated. Okay, this is the end of the problem. As I said before, we calculated the forces, internal forces and moments at the point B by doing the section there, and then we moved to the point A, did a section at the point A, and realized that we were in need of calculating that tension. And for that, we just came back and we took the possibility that we had to make to dismember this and take this part apart, because this is a pin, and we could put the two reactions for the pin there, and then we have 2 and 3 unknowns. We could do rigid body equilibrium in this element, and that allows us to calculate the tension T. I plug back the tension T in this one, and then it just put the internal forces and solve for that, and we got the values. I hope that you enjoyed this problem, and see you in the next video. Have a good day.